Today's lesson focuses on aldehydes and ketones. Aldehydes and ketones are commonly taught together because they are functional isomers of each other, which means that even though they are two different families, they contain the same functional group. And the functional group that they contain is called a carbonyl. The carbonyl group is a carbon that is double bonded to an oxygen. And where this carbonyl group is placed will determine whether you have an aldehyde or a ketone. So if the carbonyl is placed at the beginning of a carbon chain, we then have an aldehyde. So here's an example of an aldehyde. And if we saw one, let's make this right here. So this would be an example of an aldehyde. And we know that it is because we have a carbonyl and it is on one end of the molecule. It won't surprise you to hear that it would be classed as the beginning because you would always start numbering from the side closest to the carbonyl. That would be carbon 1. Remember that carbons make 4 bonds. So when the carbon is double bonded to an oxygen, that's 2 bonds taken up, and it can only make 2 more, so just keep that in mind. If the carbonyl is within the carbon chain or in the middle of the carbon chain somewhere, and you'll notice down here, we have R groups on either side, and R groups are any kind of carbons, then we have a ketone. So an example of a ketone would be something like this, and this is actually called, commonly called acetone. So many of us have heard of acetone, and this would be that structure there. And again, functional isomers, so they'll have the exact same formula between the two families, but because of the placement of the carbonyl, you get 2 different families as a result. Let's do some examples of naming of aldehydes first. So when we have an aldehyde, we're going to count the number of carbons in the longest chain containing the aldehyde group. So we know that that aldehyde group will be the carbonyl, and that carbon will always be number 1. So if I give you a structure like this, then we can look at that. We see that there's a carbonyl. It is on an end of a chain. So we know that it is an aldehyde, not a ketone. And we're going to number this. And everything in there, in that molecule, is single bonded. So this is a butane. And instead of calling it a butane, because there's extra, we lose the E and we add the suffix Al. Okay, so aldehydes always end in Al. Sometimes with your aldehyde, you can have a double bond present. So I'll stick a double bond there. I'll put the carbonyl on this side. I tend to always show the hydrogens on the end. I don't know, it's just bad habit, I guess, or old habit. You can leave them off if you want, because we don't tend to put the hydrogens in, but I do. So then we are going to number from the side closest to the carbonyl, 3 and 4, 5 carbons in this case. And if we have a pi bond, just make sure that you, again, indicate the location of that. So this is a pentene. So the pi bond is on carbon 2. So this is a pentene, and then we can just say Al. And watch your writing, okay? So OL suffix is an alcohol, AL suffix is an aldehyde, and I need to be able to read your writing and know, that you're writing it down properly. Let's do one more where we'll put some branches in, but again, nothing new here. Okay, so I'm going to put the carbonyl on the opposite end. We're going to start numbering from there. 1, 2, 3. We can either go down and over or go across. We're going to go across because if we don't, this becomes a branched branch on the end, and we want to avoid those at the moment. So if we were going to name this, this would be 3-ethyl. Put our ethyl group first because of the alphabet. 4-methyl. And then this is called a pentanal. And you don't need to say 1-pentanal because we know that's the rule. We have to start numbering on the end closest to that carbonyl group. Let's practice naming some ketones now. So now with a ketone, we are looking for the carbonyl to be within the parent chain. We're going to number the parent chain from the end closest to the carbonyl. So if we do this as our first example here, I'm going to start numbering from the left side, 1, 2, 3, 4, no branches. So all I want to do is indicate that I have a 4-carbon parent, single bonded, which is a butane. I'm going to drop the E, and then I'm going to add ONE as my suffix. Okay, so ONE is the suffix for ketones. And I also have to indicate the position number. So my ketone, the carbonyl group is sitting on carbon 2. So we're going to call this a butanone as a name, butanone. Here's another example where we have 2 carbonyl groups, but again, they're within the molecule, so this is a ketone. It won't matter what side I start numbering, it's equal to the carbonyls from either end. So we have a methyl group on carbon 3, and we have a pentane molecule, but it's a pentanone because it's a ketone, and it's a dione because there's 2 of them. So we have 3-methyl. I'm going to have to split this up, but it should be one word. And then we're going to say 2,4 pentane, because we have to keep, we have to relay the info that everything's single bonded. And then we're going to say dione. Okay, so it's important that you put the di in front of the prefix. Here's another example of a ketone next door. So we see the carbonyl sitting here in the middle of the molecule, and we also notice we have pi bonds in a branch. So after an oxygen group, a pi bond takes precedence next. Okay, so whether you are looking at a straight chain, if you had a ring structure and you had an oxygen and a pi bond, oxygen comes first, ring or pi bond comes next. So because it's equal distance to the carbonyl, okay, so 3 carbons in on either side, I'm going to start numbering from this side because this is now the end closest to the pi bond. So we're going to number it like that. And then we're going to comment on what we have going on. So I'm just going to bring a line here to kind of tidy it up. On carbon 4, I have a methyl. And then I have 1 pentene. Okay, so that's where my pi bond is located. And then we're going to split up the name 3-one. Okay, so again, no confusion as to where the pi bond is or where the carbonyl is. When we have cyclics, like this one, we still want to make sure that those branches are in lowest position order, but we have to start numbering at the oxygen. So we're going to start numbering here, carbon 1, and then we're going to move over 2, 3, 4, 5, and 6. So I have methyl groups on carbons 3 and 4. And because I have more than one, we're going to call it a dimethyl. And then I have a cyclohexanone. I can't fit it all in, but that should all be one word. Okay. You can say 1 cyclohexanone, but again, that's the only place that the carbonyl can be. So it's not necessary to state that. Let's talk about the properties of aldehydes and ketones. So we'll get to some chemical properties a bit later when we talk about reactions, but for physical properties, aldehydes and ketones have lower boiling points and a little bit lower solubility as well compared to alcohols. Okay, so because we have an oxygen, we know that that oxygen will create a polar bond, but it doesn't create a hydrogen bond like it does in an alcohol. So when we talk about the boiling points, there won't be as strong of an attraction between the molecules. There'll be an attraction to water, but not as strong as an alcohol, because again, those alcohols contain hydrogen bonding. So they have that hydrogen that is slightly positive that reinforces everything. If I look at my acetone molecule right here, my carbons that are present are all involved in non-polar bonds, except with the oxygen. Okay, so again, oxygen is more electronegative. You're going to form a dipole through the structure like that, but no hydrogen bonding. None of the hydrogens are positively charged. So if I had another propanone right next door like this, and I draw a dipole, again, they will be attracted to each other through dispersion forces. They're always attracted to each other through dispersion forces, but more so with that dipole-dipole attraction. If I look at propanal over here, which is my aldehyde, again, the only dipole I have is through the oxygen like this. And be careful because, we draw this hydrogen there, but that hydrogen is bonded to a carbon. And carbon-hydrogen bonds are nonpolar. So if you have another aldehyde, so another propanal, you only have the dipole running through, and that, of course, can attract a neighboring molecule, but there is no hydrogen bonding. Okay, so just make sure that you are aware of that. They do not contain hydrogen bonding, so they won't have as strong of attractions as alcohols as a result.